Good afternoon, everyone, and it's a great pleasure to have Hector here today with us. So Hector did his PhD with Emmanuel Barthi, and then he was a postdoc with Nick Yunes before moving to AI in Potsdam. And Hector works mostly on tests of GR and its various ramifications. And today Hector will talk about quasi-normal modes and their excitation beyond GR. So Hector, please go ahead. It's all yours.
Yeah, so thanks a lot for the invitation to give this talk, Samantha. I will cover a little bit about some of the recent work that I'm doing that has to do with quasi-normal modes and also the excitation, in particular in theories beyond general relativity. I try to keep the seminar at a level that I think I hope many of you will be able to follow, but the main thing that I want you to learn out of the seminar is that you will be able to explain by yourself what this diagram means and what are the implications of this little diagram here. So if you get to understand what this means by the end of the talk, I'll be very happy. So since the title involves beyond general relativity, let me start by giving a motivation for why I am studying theories beyond general relativity. And often I like starting from picking up this book by Robert Dicke, The Theoretical Significance of Experimental Relativity. This is it's basically a book that is a set of lecture notes that he gave at one of these Le Rouge summer schools in France. And even if you don't read the whole book at any point in your life, at least the introduction is very interesting. And he begins by discussing how difficult it is to do experimental science in our field of relativistic gravitational physics. And he goes on and saying that performing experiments that involve gravity is very difficult because the gravitational force is much weaker than all the other forces that we know of. And the real place where the gravitational force is the dominant one is only when we go to astronomical scales. And he goes on a little bit more and tries to identify what would be a very good system for you to do experimental relativity. And he comments out that it would be very nice if we could take two bodies of 10 to the 33 grams of mass and of a density of 10 to the 6 grams per centimeter cubic and whirl them about each other at a very high speed. Now, the experimentalists cannot do this in the laboratory, of course, but if we just look hard enough, we may be able to find nature performing these experiments for us. And then he, towards the end, he comments that, well, experiment and observation can become intertwined in this field of gravitation and will probably become more so in the future. So while we have the problem that we cannot reproduce experiments in this field, like just as we would do in a laboratory, if we just look out there hard enough, we may find many of such experiments being performed that might be suitable for what you want to understand about gravity. And I don't really have to tell you that several, well, about 100 of such experiments have now been seen through gravitational wave observations of compact binaries. So the coalescence of binary systems where you have either a black hole or a neutron star composing the system. So we really now entering a new era in experimental relativity. Now, even though Dicke in his introduction was talking about neutron stars, unfortunately, neutron stars introduce additional complications if you want to do experimental relativity that have to do with the fact that we really don't understand very much about the behavior of matter at very high densities. So to some extent, it's natural to consider black holes because they are slightly simpler systems. Well, not slightly, but considerably simpler systems And as you know, to describe a black hole, all that you need is really your notions of space and time. So the coalescence of a binary black hole can, just to give an overview, you start with this slow wind spiral where you have the two black holes orbiting with, with small velocities in comparison with the speed of light, and they slowly radiate energy and moment away from the system, making the orbit shrink, bringing the two black holes closer and closer together. There'll be a moment where they will be so close to each other in which this quasi-adiabatic evolution breaks down, and then the two black holes really plunge into each other with high speed, like a fraction of the speed of light. They merge to form a single final object, and then this remnant radiates away these perturbations in the form of this thing that we call quasinormal modes, and it's what we call the ring down. And then with the observation of subsystems, you may ask yourself, well, would it be possible for us to use the signals to try to detect for any deviation away from the predictions of general relativity that I'll call GR from now on? That would be the black line here, and maybe measure any new physics beyond general relativity that will be qualitatively shown by this colored lines here. Right? And the idea here is that I will focus on the ring down. Partially, the reason for this is that the remnant object, if you're interested in the ring down, you're essentially studying a one-body problem rather than a two-body problem, as you would have to do here. And the system is somewhat clean as well. Now, as I already alluded to, black holes are very simple, at least in general relativity. There are mathematical theorems that you can prove, which prove the uniqueness of the black hole solutions of general relativity, that state that they are described by the Kerr-Newman family of black holes. So rotating black holes that are fully described by the mass, the spin, and possibly an electric charge. The electric charge is often thought to be not that important for astrophysical considerations, but in principle it could be there, but I'll focus only on mass and spin. And this kind of theorem, you can think of it as there's this cartoon that I took of one of the papers by Vishweshvara, in which he argues that the existence of this no-hair theorems, as we call them, they are, in a sense, the ultimate application of this idea of the Occam razor in physics. So basically, in this no-hair theorems, you're saying that all the information about the progenitor of the black hole is lost, except for the mass and the angular momentum of the initial distribution of matter that formed the black hole in the end. And one of the things that I found very amusing when I was using this cartoon, I've used this many times before in my talk, but I noticed that if you look close enough at the black hole, it actually has two hairs only. It has two streams of hair, which I think were meant to represent the mass and the spin of the black hole. So then, with one of the consequences of this no-hair theorems is that the perturbations of the black hole, they will inherit this dependence on the mass and the spin. And then you can entertain the idea that if I have the observation of the ring down, at the end of the coalescence of two binary black holes, I can use the information about contained in the ring down to try to infer the mass and the spin of the remnant object. So this goes under the name of black hole spectroscopy, which is very similar to how the name borrows from atomic physics, where we can identify elements through the analysis of the spectral lines. So here you would identify the black hole through its quasinormal-mode frequencies. So as I said, each of these quasinormal-mode frequencies, They are complex numbers, and they are labeled by these indices here that have to do with, I'll get to this in a moment, but take them to be a complex number. And they depend only on the hole's mass and spin. So if you have a single measurement of this number, because it's a complex number, you will have two lines that you can draw in a mass spin plane, for example, like this. So say that I measured experimentally the quasinormal-mode with these indices here labeled 2 to 0. So from the real part that has to do with how much this mode vibrates, I would get a curve like this. From its imaginary part, that gives me information about the rate at which the mode damps, I would get this other curve. And from the intersection, if the predictions of general relativity are correct, this will intersect at some point, and this will give me information about the mass and the spin of the object. And if for some reason I'm able to measure any additional quasinormal-mode frequency from my data, this will give me additional curves. So for example, now I have another mode, and I'm taking the real part of it. I would get another curve here, which, if everything is consistent with general relativity, you would expect that all the curves would intersect at the same point. So all the curves would intersect at a single point, and therefore this would provide you a test of general relativity. This thing is very similar. You might have seen something similar to what people in the binary pulsar community do. And instead of quasinormal modes, you have this post-Keplerian quantities, but the idea is very similar. And then the hope of this program is that with the direct evidence, as quoting from that file, is that carrying on this program, we would have direct evidence of black holes with the same certainty. Let's say the 21 centimeter line identifies interstellar hydrogen. So that's the idea behind black hole spectroscopy. Now, so far we have seen at least a handful of events with the LIGO, Virgo, and Cagra detectors that allow us to infer at least this quasinormal mode labeled by this index 2 to 0. And there have been claims in the literature that we have seen additional modes. But at the moment, I think it's fair to say that we can only confidently say that we have detected the fundamental quasinormal mode. Okay. So what is the particular problem that I am interested in? Quoting back from Diggers. So the type of question that you can make that I'm particularly interested in is in how different are the quasinormal spectrum relative to Kerr when you have a black hole solution, which is not the Kerr family anymore. And sub-questions that go into this are, for example, what is the dependence of the quasinormal mode frequencies on new couplings that your beyond GR theory introduce? What is the dependence on any extra fields that your theory may introduce, and also on the black hole spin? There is also a symmetry, which is very particular to the quasinormal mode spectrum of Schwarzschild black holes that I will explain later, that is in general broken once you go beyond the Schwarzschild solution. And a second question, which is related with this, and it's also related with whether you can detect potentially these modifications to the quasinormal mode frequencies, is what is the amplitude with which these quasinormal modes are excited given some source of perturbation of black holes, right? So imagine that you have the black hole, I perturb it. I know that the response will be given by certain frequencies, but what is the amplitude with which these frequencies are excited with? That's a question that you have to address if you want to claim that anything will be observable in gravitational wave observations. This is a question that remains open even in general relativity, as far as I know, for the case of comparable mass binaries, but it is possible to do some computations in the limit of black hole perturbation theory, where I take one of the bodies to be much less massive than the other, and I'll tell you a little bit more about this as we go on. So the plan for today is to give a partial answer to some of these questions following this recent preprint that I put out in collaboration with Giovanni Tambalo, Kostas Lampedakis, Kent Jager, and Jan Steinhoff. So that's the very broad overview of this topic. So the outline for the remainder of the talk is the following. I will talk about this affected field theory of general relativity, which is the particular model of beyond general relativity theory that we use it to perform this calculation. I'll give you a little bit of an overview of what it is and why we chose to work with this particular extension of general relativity. I will then give you a little bit more information about quasi-normal frequencies. I'll talk about the excitations, and then at the end I will go on and summarize and share some thoughts. And if you have any questions, feel free to interrupt me. So, okay. So the model that we decided to work is this affected field theory of general relativity that was basically introduced by Gorbenko and collaborators, but there has been several papers on the subject, including by groups by Claudia Deram and Pablo Cano. And there's a typo here. And basically the idea is that you want to include, on top of the usual Einstein-Hilbert term, all possible contractions of the Riemann tensor and its contractions systematically in an affected field theory approach. You can show that if you're building the CFT around vacuum, the first non-trivial contributions appear at this cubic order, where you have the Riemann tensor contracted with itself 2 times. And there's this other term where you have 2 Riemann tensors, and this R tilde is the dual of the Riemann tensors. It's a particular combination of the Riemann tensor with the totally antisymmetric Levi-Civita tensor. So and associated with these terms, you have a new length scale or an energy cutoff on the EFT that is set by this length scale L. And you have this 2-dimensionless quantities, lambda E and lambda O. The reason for the subscripts is that this term preserves parity if you were to do a parity transformation. So this is a parity even term, we call it. And this term violates parity, and we call it parity odd. So that's the reason for the subscripts here. And we thought that this is a useful model to address the questions that I presented to you 2 slides ago. So why is that the case? Well, first is that by construction, the EFT does not contain any additional fields that, in addition to the metric that would only make the problem more complicated. So often when we talk about extensions to general relativity, we typically invoke theories that have scalar fields, vector fields, or additional metric fields. But to keep things as simple as possible, we're working with this one that only has the metric. Generically, the addition of scalar fields or whatever other fields, they only make the problem more complicated than necessary, at least the problem that, and the questions that we want to address in this line of research. And we can treat everything perturbatively in this lengthscale. Okay. There's only two dimensionless parameters, lambda e and lambda o, that are introduced to you. So, the parameter space of the model is not that large. And it is known that we can find analytic, including rotating black hole solutions out of this theory. Meaning that in principle, you can compute, you have the background computed analytically, you know how to apply the formalism of black hole perturbation theory to it. So in principle, you can address all the questions that I listed 2 slides ago from first principles. Like you can, have all the steps clearly defined on how to compute things. But that makes it, from my perspective, a very useful, this type of theory, a very useful toy model to address these questions.
Hector, if I may.
Yes.
Yeah. So here, for example, I mean, why r squared terms are absent?
Yeah, so the r squared terms, you would have 3 possible combinations. So there will be a Ricci scala squared, a Ricci tensor squared, and the Riemann tensor squared.
One of them can be removed by this Gauss-Bonnet criteria, right?
Yes, exactly. Now, if you truncate with this, only with these 2 remaining terms, whatever you choose, you would, in general, have a theory that has, higher order derivatives.
Okay.
And this introduce new degrees of freedom. And it is not that some of this, they actually behave as ghosts. But if you were to treat things as perturbatively, and you wouldn't have this problem. And I also mentioned that we are working in building the EFT around vacuum GR, so the Ricci terms would be vanish in the background.
Yeah, but by that argument, like the r which is here, that should also be set to 0, right? I mean, so. I mean, are you putting that condition on shell or off shell?
On shell or off shell? Can you explain what you mean?
I'm saying, like, suppose I have r squared in the action. Now I can say, since in vacuum r is 0, so r square should not contribute. That would be an, I'm using the fact that in the action itself. On the other hand, I can get the equation of motion and then see whether r equal to 0 is indeed a solution. So I'm just trying to say whether these 2 approaches are in general different, right?
Yeah. Yeah, you think you do use the solutions of the in order to eliminate.
Sure. And another thing, Hector, is that, I mean, if you are saying about this ghost instability, then I think you only have the Lovelock class, right, which has second order field equations. I mean, any other theory of gravity would have higher order field equation. But except for Einstein-Hilbert, any Lovelock order is a total derivative. So the term that you have added, that is also probably a higher derivative theory, right? I mean, I'm not sure.
Yeah, this theory, if you were not to treat it perturbatively in L, yes, it will be of higher order, and it will probably involve some ghost degree of freedom.
I see. Okay, thank you.
The key point is that we treat this perturbatively, and in this case, you don't have this problem.
I see. So that means you will only keep terms up to L to the power 4, right? Because that's what appears in the action. That is the idea.
Yeah, and then we keep the.
Okay, thank you.
But in principle, one could also work out what you would have if you were to include Riemann to the fourth and so on. And in fact, I think that was the original model that Gorbenko Rao used. But then there are some papers by Deram and collaborators pointing out that those terms can also be included.
Okay, thank you.
Okay. Okay, so we want to simplify the problem, but of course you don't want to simplify too much. So when you want to make a spherical cow out of your problem, you still want to keep a little bit of cowness into it. You don't want to treat a perfect sphere. So I'll make some additional assumptions just to start off. So I will consider only the parity even term that I'll just call lambda from now on. So I will put this other term equal to 0. This parity violating term introduces a lot of interesting new features that we can discuss at the end. But for simplicity, I will work only on the parity even sector for now. So I only have Ricci plus the Riemann cubic from now on. And then we are going to consider non-rotating black holes. But in the sense of not simplifying too much, we will consider the gravitational perturbations of the system. So by gravitational perturbations, I mean that I will treat the space-time metric to be that of the non-rotating black hole solution, and I will perturb it with some H mu and apply the formalism black hole perturbation theory to analyze the dynamics of this H mu. Now, if you are to carry this procedure, you end up with an equation that has this form in general, and I will explain in some more details what this equation is about. Okay, so let's unpack the main equation that we are going to study from now on. So this psi is, we normally call it as some sort of master function, which is just a particular combination of the metric perturbations, okay, which have been decomposed in this thing called tensor harmonics. That, if you don't know of, just think about it as a sort of generalization of the usual spherical harmonics. That's why you see the indices L and M. And we had also gone to the Fourier domain, meaning that I decomposed all my modes in this way. This is the convention that I'm using. This quantity x is just a coordinate that we call Toto's coordinate that maps the domain between the event horizon of the black hole and up to infinity into this new domain that now spans minus infinity to plus infinity. And this function q that appears here is a function that is in general position dependent. It can depend on the frequency of your mode and any other parameter, theta, for example, the length scale L in our EFT, or an electric charge if you were considering a charge of black hole and so on. And yeah, so this is what the function q is. Now, once you have that composite, you have written this equation, if the function q has this property, so that it asymptotes to omega square at the two edges of your domain, the general physical solution of that equation has this form here. So you would like the solution to be purely ingoing at the event horizon. Remember that this coordinate x pushes the event horizon to minus infinity. And in general, as we go to plus infinity, the solution will be some superposition of modes which are ingoing into the black hole and outgoing to spatial infinity. Now, the quasinormal modes are particular solutions of the problem for which this ingoing amplitude is equal to 0. So they describe waves which are purely ingoing to the event horizon and purely outgoing at spatial infinity. There is a nice analogy that you can make with wave scattering, well, rather connection that you can make with wave scattering, which is that once you have in wave scattering, you can define something which is called the scattering matrix, or the S matrix, which is normally given by, the ratio of the outgoing wave and the ingoing wave in this way, or that you can write in this way. This is the phase shift function. So you see that you can think of the quasinormal modes as being complex valued poles of the scattering matrix, given some value of L or M. This means that the computation of the quasinormal modes is essentially a boundary value problem, where you want to find when 1 over the scattering matrix is equal to 0, once you fix the multipoles and all the other parameters that you have in your Q function. Okay. So let me give you an illustration of what this looks like for the Schwarzschild black hole, which is the simplest solution, and then also in general relativity. So when you're studying the perturbation of the Schwarzschild solution, you have 2 copies of that equation that I showed to you, and they are associated with the 2 degrees of freedom that you have in general relativity. One of them has to do with metric perturbations that behave in a certain way under parity transformations, and we happen to call them axial perturbations. And the Q function has this form here. And then there's a second equation associated with metric perturbations that transform in a different way under parity transformation, and we call this the polar perturbations, and the function Q is given by this. So from now on, I will use minus and plus to denote things of axial and polar parity. And these functions here, they are the potentials that you usually associate with the names of Reggie Wheeler and with this fits here. This, you see that there's no dependence on the multiple number m, because the problem has spherical symmetry. And the only thing that you have is this L, which for gravitational perturbations varies between 2 and infinity. So the lowest order one is the quadrupole perturbation. And from now on, I will call V this particular combination. So these are the potentials. And you can clearly see that this satisfies those conditions on Q, that it approaches omega squared at minus and plus infinity, because when x goes to minus infinity or towards the event horizon, this function is equal to 0. So you have only this bit. And when you go to plus infinity, all of this vanishes and you only have this thing again. So that general physical solution that I showed in the previous slide is a solution of this equation. So there's something which is very interesting, that even though the potentials look very different in the functional form, if you are to plot them, they actually look very, very similar. So this is a plot of the Reggie-Wheeler and Zerilli potentials that I just showed to you for the L equal to multipole. And I'm plotting this in tortoise coordinates, so the event horizon is to minus infinity, and spatial infinity is here. So you see that the 2 potentials have about the same size, same magnitude at the peak, and they just shift a little bit where the location of the peak is. But in any case, both of them are very close to the light ring of the Schwarzschild spacetime, which is a 3m, which in tortoise coordinates is roughly 1.6. Now, there is more to this similarity, in addition to them looking very similar, that there's something which is very funny, that if I take those 2 potentials and I do an integration over the whole domain where they have support, right? So minus to plus infinity, you find that they're actually the same. So if you take those two complicated expressions, you integrate from minus to plus infinity, you do the calculation analytically, and you find that they are the same. And there's more to this, because if I take the square of the potential and I do the integral, I find that they are the same again, where P is just this particular combination of L. They are the same. And you may wonder, well, I'll keep carrying this game and I will take the cube of the potential and then integrate. But it turns out that you don't get the same result then. But you do get the same result if you take twice the cube of the potential plus its derivative. And then if you integrate this from minus to plus infinity, you'll find that the perturbations of polar and axial parities, they are the same again. And this game can go on. So the next term in this hierarchy of integral identities will be this particular combination. The next one will be this much more complicated combination here. And it goes on infinitely. So this actually is a result. There's an interesting consequence of this, of these identities, which was found by Chandrasekhar in 1980, in which he argued that if two potentials are to have the same reflection and transmission coefficients, like thinking in terms of a wave interacting with these potentials, they must satisfy an infinite hierarchy of integral identities, in which the integrants, so the things here, they are somehow related with the Korteweg-de Vries equation, which is related with integrable systems, and it's used to describe nonlinear waves such as solitons. Frankly, I don't fully understand the connection yet, but I'm pointing this out to maybe someone will notice a little bit better, and maybe we can discuss. I would like very much to learn more about this. But for our purposes, one thing that is important is that, as I mentioned to you, the quasinormal modes, they are associated with a pole of the S matrix, which has to do with ingoing and with wave scattering in the potential. And one consequence of the two potentials having the same reflection and transmission coefficients is that the quasinormal mode spectrum is the same for the perturbations of plus and minus parity. So here I'm adding additional indices, but yeah, we only have L in the case of Schwarzschild. All the N's are degenerate, and N, I forgot to mention, is this thing called the overtone number. Basically, in the quasinormal mode spectrum, once you fix L, you have a number of solutions. And if you sort them out by the decay rate, the lowest, the one with the longest decay rate is the fundamental mode, so it will correspond to n equals 0, and then n equal 1, n equal 2 corresponds to modes that decay faster and faster. So there's for each L, there's an infinite number of such photons. So this is an interesting property that is very particular to the Schwarzschild solution, and that we call isospectrality, meaning that the spectrum are the same as two modes of perturbations. So what happens in the EFT? So you can do the same calculation that I sketched very briefly in the previous slide. And the equation that you end up has this form here. So you have two equations again for each of the parities, plus and minus, and you have this speed of sound here. So the effective potentials, they basically get corrected by terms of order L to the 4, which is the order at which the Riemann cubic terms enter in the Lagrangian. One thing that you can check is that the tower of integral identities that I showed to you in the previous slide breaks down already at the first one. So if I just were to integrate the corrected EFT potential over the full domain, I find that the integrals are not the same. They are broken. The equality is broken by a term of this order, which is sufficient for you to conclude that the spectrum cannot be the same anymore, meaning that you have this breakdown of isospectrality in this EFT, and this is something that was known by these people. And in addition, the perturbations have a position-dependent propagation speed, which deviates from unity very near the black hole horizon. But as you go to spatial infinity, the modes propagate with the speed of light. So one of the consequences of this, and this is the cartoon that I had on my title slide, is that if you start with a quasinormal mode here, say in the complex plane, so you have the GR solution somewhere in the complex plane. If you start cranking up the EFT corrections, the two modes will branch out, the ones of polar and axial parity. They will split because the symmetry is broken. And as you increase the value of your EFT corrections, these two quasinormal mode branches of solutions that will move along in the complex plane. So that's the image that I had at the beginning. So the expressions for the effective potential, they are rather long, so it's better to have a plot of them. So this is what they look like for the polar perturbations and for the axial perturbations. Epsilon is basically the dimensionless combination of lambda times the length scale to the fourth power divided by m to the fourth and the mass of the black hole. And I'm varying, so the GR potential will be the black curve, and I'm varying epsilon in this range here. And you see that the modifications to the effective potential, they are basically confined to this near horizon region and a little bit on the peak of the potential, as you can see here. And as we move to spatial infinity, the curves all merge together into the GR one. And this is somewhat expected because the corrections that we are adding to the theory, they are higher order in curvature, so you would expect that any significant effect of these terms will be confined to the near horizon region of the black hole, which is indeed the case. And this reflects into the shape of into the effective potential, where the deviations are larger, so it's always near the horizon. So one thing that we did in this work was to compute to explore the quasi-normal frequency spectrum. So previous works had done partial computations of this, but perhaps for technical reasons, they had studied only the fundamental modes, so the n equals 0 quasi-normal mode. And in our work, we went beyond this calculation by applying a method that I can explain in more details afterwards, that involves working with some, they're called phase functions that you can then integrate in a certain way on the complex plane. So you do some sort of analytic continuation of your equation, and you do an integration along a certain path in the complex plane. And this resolves this bypasses some difficulties that one has when computing quasi-normal modes. But this is a little bit technical, so I'll rather just focus on the results. So yeah, so here we have in the complex plane, as I said, people had done these computations here before with this method that I very sketchily told you we computed the first overtones. And as you can see, as I increase if I fix the multiple number, as I increase the overtone, you see that deviations from the GR value, they are larger and larger. And in some sense, the overtones, they are more sensitive to this corrections due to the Riemann cubic term than the fundamental mode, as you can clearly see here. As I also said, this symmetry between the quasinormal modes of polar and axial parity are broken, so now they move away in the complex plane. The overtones, they seem to be more sensitive to the length scale L. And after a certain point, this all the calculations are done to leading order in epsilon. Remember that at the beginning we were discussing that everything has to be expanded in powers of L to be within the EFT regime. So there is some point where these things become non-linear, as you perhaps most clearly seen here, like that the curve bends, so you cannot approximate this by a straight line. And it means that this approximation is not really valid beyond this turning point here, for example. And very importantly, the value of epsilon for which this nonlinear behavior kicks in depends on L and N. So, well, you can clearly see here that for some small value of epsilon, this curve is not deviating linearly anymore from the black dot, while here the same orange curve behaves linearly for this full range of values in which we did the calculation. So there's a dependence on L and N. Now, this has some interesting consequences when you start thinking about what is the meaning of, what is the physical interpretation of the overtones and how this ties with our description of our theory as an affected field theory. So I told you that at the beginning that the real part of the quasinormal mode has to do with the oscillation frequency. But in reality, this is only true for low frequency modes. For low overtones, in which in general the real part of omega is much larger than the imaginary part of omega. And there is something that is very funny about this. So if I were, so let's look at this plot here. So here I am plotting the quadrupole QNM, so L equal 2 is and N, so the overtone number N. And I'm plotting the real versus the imaginary part. And this is for the Schwarzschild solution in general. Okay. So you see that contrary to the thinking that you would say, well, if overtone frequency should be, if you think, okay, so let's think about a vibrating string, for example. So the fundamental mode will be a mode with no nodes. The first overtone will be the solution with one node, and so on. And as we increase the overtone number, the oscillation frequency associated with these modes is higher. But actually, for the quasinormal modes, that's not quite true. You see that for low overtones, the real part actually decays as you increase the overtone number, which are these dots here. So it's exactly the opposite of what you would expect from thinking in analogy with a vibrating string. And in fact, there is even one point in which the real part is equal to 0. And if you go beyond this point, you will think, well, maybe at this point here, this physical interpretation kind of works because I'm increasing the overtone number and the real part is increasing. But then you see that there is kind of a plateau that is reached past this point. So yeah, so our intuitions don't really work very well on this. Now there is an interesting work by Jordan where he argues that if you want to think of the quasinormal mode frequencies in terms of a damped harmonic oscillator, the frequency that you would have to associate with this damped oscillator is actually a combination of the real and imaginary parts in this one. And if you were to plot this as a function of the overtone number, you do recover this this picture, this qualitative picture that you would expect of the problem, that as we increase the overtone number, the oscillation frequency of the mode grows. So once you come to think that, well, if I should introduce a frequency scale with the quasinormal modes, if I want to investigate what is the regime of validity of the EFT, I'm basically introducing a new length scale that I should take into account, right? So at the level of the black hole, we want L over m, so the mass of the black hole, to be much less than 1 for us to be within the regime of validity of the EFT. But if now, on top of this black hole spacetime, I'm adding small perturbations, I want the wavelength of these perturbations to also be smaller than the length scale associated with the higher curvature corrections for you to be within the regime of validity of the EFT. And this basically translates into this condition here that in addition to this parameter epsilon that has to do only with the mass of the black hole, I also have some parameter epsilon f that has to do with the frequency of the perturbations to the black hole. So these are two length scales that have to be taken into account when interpreting the results of your numerical computations. And another thing that comes out of this is that once you think of the overtones as high frequency waves, you can kind of understand why they are more sensitive to this near horizon corrections, because being higher frequency waves, when they interact with the potential, they probe deeper into it, right? So they can really propagate into the past the effective potential and see what is happening near the horizon of the black hole, which is precisely where these corrections from the higher derivative corrections become more important. So that's qualitatively why the overtones are more sensitive to these corrections. Now, if you push this a little bit further, it leads to some interesting conclusions. So there's one computation that you can do in general relativity, which is that analytically you can compute what is the quasinormal-mode frequency in the limit as the overtone number goes to infinity. So the result is this. So when n goes to infinity, this is the real part. It approaches a constant. And the imaginary part has this form. Now, if I use those inequalities involving epsilon f and an epsilon, so the two-dimensional scales that you have to take into account to be certain that you are within the EFT regime of validity of your theory, one finds that if you take it to be 1, which is exactly when the EFT breaks down, it doesn't make sense to talk about overtones of n beyond 25. Basically because you go outside the regime of validity of the EFT. If the overtone number is larger than 25, approximately. So this has the consequence that you cannot describe the full quasinormal-mode spectrum within the EFT, which to some extent again makes sense qualitatively once you start thinking about this, because as you go to n going to infinity, you have waves with shorter and shorter wavelengths, and eventually you break down the description of the EFT. You're going more and more into the ultraviolet regime of the theory. So you go beyond the EFT. You may object and say, well, 25 is too high of a number. It it does not matter in real life. But I don't think that is necessarily the case, because this number comes from when epsilon is equal to 1. But in practice, when you build an EFT to describe a certain physical system, it's ultimately comparison with observation that tells you when the description breaks down. So in principle, this could be at a much smaller number, as long as it's larger than 0 and small. As long as it is larger than 0, it can pretty much happen anywhere. So it could be that even for astrophysical scales, maybe for some very small value of epsilon, it really doesn't make sense to talk about overtones past a number which is smaller than this. And if that's the case, it could be that this fact here could have some implication for this program of black hole spectroscopy that I mentioned in the introduction. And then you may ask, well, what happens then if I outside the regime of validity of the EFT? Well, in that case, you would require the ultraviolet completion of your affected field theory to be able to say anything about what happens once the EFT breaks down. Which is quite interesting, because then it raises the question, can overtones be used as probes of the ultraviolet completion of general relativity? I'm just speculating a bit here, that this is what comes out if you push this argument to its limit. So this is a sort of a little cartoon to illustrate, to summarize all of this discussion. So here I'm plotting that frequency that involves the real and imaginary parts of the quasinormal-modes of the previous slides. You can sort it out by the overtone number. So this is the fundamental mode, and infinity goes up here. On the x-axis, you have the parameter that controls how large are the magnitude of this higher derivative correction. So here it's equal to 0, so general relativity. So you keep, as you move towards the right, there's the splitting, the breakdown of isospectrality, so the curves go like this. Once you reach epsilon equal to 1, the EFT doesn't make sense anymore, so this is the shaded region, so we cannot really tell what happens beyond this. If I use that additional condition, that the dimensionless parameter associated with the wavelength of your quasinormal mode must be less than 1, you get this additional curve. That, as you can see, as you increase n, it moves towards smaller and smaller values of epsilon, meaning that eventually you will just hit here. And this is where this number comes from. So if I were to extend this up to 25, this shaded area would approach this point here. And this dotted line has to do, and I really didn't explain much about this because of the interest of time, but it has to do with when the linear approximation in epsilon breaks down, which is an approximation that we use in our calculations. So you see that it also breaks down as you increase the value of the overtone number. And this is basically a summary of all of the discussion that I had here. The dotted line here has to do with this idea of soft UV completion. So it's basically an argument that is put in this by Planck et al. That after you go past the EFT, the regime of validity of the EFT, you want the corrections to kind of flatten out and don't keep growing as you keep increasing this parameter, and that's why this curves flatten out. But the main message here that I want to convey to you is that once you interpret your results from EFT perspective, there's you naturally led to the conclusion that you cannot talk about the full QNM spectra as we do in general relativity in the VFT. So I think I'm reaching towards the end of the hour, but I have 3 more slides and then I'll close. So let me talk to you a little bit about the excitation of the quasinormal modes, which is related to the second question I had in mind at the beginning of the talk. So now we are interested in an equation which is just like the one that we saw before, but now I have a source term S. And one can show, Lever in particular did this in the late 80s, that the contribution to the time domain signal can be written in this way. So you sum over all the quasinormal modes. So there's a sum over the overtone number once you fix L and M. And each of these quantities, they come with a coefficient C that we call the excitation coefficient. Okay? And this excitation coefficient, it can be decomposed into 2 parts. There's one part that only depends on the black hole geometry, which is what we call the excitation factor, and we denote this by B. And this is multiplied by a term that does depend on the source that is perturbing the black hole, which is the source-dependent part. And the product of these 2 quantities gives you this excitation coefficient, which is the amplitude with which each quasinormal mode overtone contributes to the final time domain signal. So just to give an illustration of this, this is a plot taken from the paper by Lever from 1986, where he is showing, as a function of the retarded time, the solution of this psi function, which is the ZD function in particular, measured at some observational radius very far away from the black hole, as a function of this retarded time. So the black line here is the solution that you would get in time domain by like evolving this equation as a PDE, if you were to go back in the time domain. Or, for example, if you were to analyze this in the frequency domain by using Green's functions, but this is what you would get. Now, if I were to use this description here, which is the contribution of the quasinormal modes to the time domain signal, and I include only the fundamental mode, you would get the dashed line here. Okay. So as you can see, it does describe quite well what you see at the ring down of the signal. It doesn't describe very well what happens in this part, and that's fine because this is only the contribution from the quasinormal modes to the full signal. So it's not expected that this will reproduce the signal at this point. But if you keep including more overtone numbers here, so I think you would get this curve here. So I think this one he had included up to 6. I could be wrong, but it's about 6 overtone numbers. And you see that you get a much better agreement with the time domain signal. So in a sense, the overtones, they do have a contribution, at least in linear perturbation theory, to that is really important to take into account if you want to describe the full signal. Now, in this work, we didn't compute the source-dependent part, but we did compute the excitation factors. And that gives us a little bit of intuition of what this breakdown of isospectrality can cause, what it can lead in practice. So I'll tell you a bit about this next. Yeah, and for some reason also, the excitation factors, at least as far as I know, they had never been computed in any beyond general relativity space-time, and I don't know why that wasn't the case. So we did this computation. So this is what the excitation factors look like. So I'm showing only for the quadrupole, so L equal 2, and for different overtone numbers. And I'm showing both the excitation factors associated with perturbations of polar and of axial part. Again, the dots are the values that they have in geometry. So just to explain what is happening here, let's focus on this one because this corner is too busy. So for the n equal to overtone, even in the limit of general relativity, you see that the excitation factors, they do not coincide. But that's something that one should have in mind, that even though the quasi-normal-mode frequencies are the same between the two parity sectors, the associated excitation factors are not the same. And again, if you increase the parameter of the EFT, you get that the curves move away from the AGR values in the complex plane. And the higher the overtone, again, the larger are the deviations with respect to general relativity. So you can see that the n equals 0 is kind of hidden here. But you can contrast this with the curves corresponding to n equal 3 that they deviate a lot. With this, you can compute something which is called an effective gravitational wave amplitude, that basically involves taking this excitation factor, combining with the value of the quasi-normal-mode frequency, and kind of use the excitation factor to give a representation of the amplitude of the wave, and use the QNM to the quasi-normal-mode frequency to describe the decay and oscillation rate of the signal. If you do so as a function of using the values that I showed to you in the previous slide, and you do this as a function of the EFT parameter, you find that for the 2, 0, so the quadrupolar fundamental mode perturbation, that this effective gravitational wave amplitude for the polar modes dominates over the ones of axial parity. There's an interesting crossover that happens at some value of epsilon in which the dominance changes. Now, since the EFT kind of let me see how I phrase this. Yeah, so since the EFT has a domain of validity, say for small values of epsilon. For example, if you were to truncate here, you would find that, at least in this approximation, where you can describe the gravitational wave amplitude without computing the source dependent part, that in this approximation, the polar QNM would dominate over the axial one. So it means that if you were to reconstruct a time domain signal, the amplitude associated with the waves of polar parity will be slightly larger than the ones associated with the ones of axial parity. Now, this is not a full answer to what would happen. It's not a full answer to the question of how having these two branches of quasi-normal modes into the signal, how they modify the signal, but at least is a partial answer to that. To really answer this question, one has to compute, in addition to the excitation factor, the other term that I mentioned to you that involves the source of the perturbation. And as I said, the product of these two things is what gives you the coefficient the excitation coefficient. Ultimately. But this is what we want to do in a follow-up. In a follow-up book.
Okay.
So I think, yeah, so this is so let me just summarize the conclusions. I hope to have convinced you that in testing general relativity with the ring down, it is not sufficient to only compute the quasinormal-mode frequencies. It is also important to understand the excitation, because that is related with the amplitude with which the quasinormal-mode frequencies appear in the time domain signal. So you really need to understand these two things. I presented you the first results of a systematic study that we are carrying in a very simple toy model of this EFT of general relativity. And even in this very simple toy problem, we found a couple of interesting things. As I told you, the overtones and also the excitation factors, they are more sensitive to the lengthscale, to this new lengthscale introduced by the EFT in comparison with the fundamental mode. This forced us to think a little bit more about what it means to be within the regime of validity of the EFT. Then we came to the conclusion that when you cannot really describe the full quasinormal-mode spectrum within the validity of the EFT. And I presented to you a very preliminary study about what this breakdown of isospectrality would imply for a gravitational wave signal. Now, one thing that you might have noticed is that when I was describing these two results, when I'm explaining qualitatively why the reasons for this, all of this really relied on thinking about high frequency waves and having a space-time that is modified near the horizon due to some new length scale that we introduce in your theory. So it's actually not very far-fetched to expect that any theory that goes beyond general relativity by the inclusion of new length scales, which are tied with some higher curvature term, they would share the same properties that we have seen here. In particular, if one were to compute, say, the overtones, they will be more sensitive to the new length scale. And yeah, it seems to be a very generic feature from any extension of general relativity. And in fact, there is another paper that came out recently by Hirano and collaborators that were also led to the same conclusions. In particular, they also analyzed some theories that have scalar fields coupled with higher derivative operators, and they also found that the overtones are more sensitive to the new length scales introduced in this phase. So this seems to be a very generic thing that you can conjecture to be true for a broad class of theories of gravity. And yeah, this is the last thing I wanted to say, and thanks again.
Thank you a lot for your Hector, for your very nice presentation. So if there is any question, maybe the audience, you can unmute yourself and ask. So anyone in the audience? Yeah, go ahead.
Yeah, so hello Hector. So it's a great, wonderful talk. Thanks for sharing your knowledge. So the basic question I have is, why does the merger, after the merger, why does the black hole needs to ring down instead of keep ringing itself for a period of a very long time? Why does it ring down? Why does it damp?
Okay, so the question is why the black hole rings down after the merger. So that's basically because the solutions, these black hole solutions are stable under perturbation. So for example, if I were to compute a quasinormal-mode and I find that it has an imaginary part with a sign such that it will cause the mode to grow exponentially in time rather than decay exponentially in time, you would find that the solution is unstable rather than stable. So essentially the fact that it rings down has to do with the fact that the solutions are stable to perturbations. And does that answer the question?
Thank you.
Yeah.
Yeah.
Any further questions?
Hello, Dr. Silva. It was such a nice talk. Thank you for sharing your knowledge. I did actually read your paper once it came out on arXiv, and the work is very interesting. So what I wanted to know from you is this phase amplitude method that you are using. I got to know about it only when reading your paper. Can you please highlight for me when does it become useful to move to such a method, say for, after deviating from, say, the WKB approach? When does it become useful to use the phase amplitude method for black holes?
Okay, thanks for the question. So we use this phase amplitude method basically for two reasons. So, okay, I'm just thinking a little bit on how to explain this and don't go excessively technical. But let me just go here. Sorry, where is the... Yeah, okay. So there is one difficulty with the computation of quasinormal modes which is that if the mode is stable, so the perturbations would decay in time, as we just discussed in the previous question, you would find that the imaginary part of the mode is negative, at least in our conventions for the Fourier transform. Meaning that the quasinormal mode wave function is actually divergent at, if you were to substitute here, in here, a mode with imaginary part negative, you would find that the mode is actually divergent at minus and plus infinity. This is not really a physical problem. You can consider different spatial slices for which you contain these divergences. But from a practical point of view, the fact that you have to resolve in your computation of the modes, which is essentially a root finding process, you have to resolve a mode that is exponentially decaying from an exponentially increasing mode when you're outside the root, right? So this is a problem this is a difficulty that the usual method that people use to compute the quasinormal modes, which is often called direct integration method, which involves integrating the solution from minus infinity up to a matching point, and then the solution from plus infinity down to the same matching point, and demand that a certain combination, the Vronsky is equal to 0. And this method that is commonly used and was to some extent used in the previous works that I mentioned, they're not very good to compute overtones. Now, the phase amplitude method has the advantage that numerically working with the phase functions rather than the master variable psi is numerically a little bit nicer. So instead of working with second order differential equation, which is linear, you end up with first order nonlinear differential equation, which is a little bit nicer to integrate. And then there is this additional step where we do an analytic continuation into the complex plane. And basically, the integration path is such that you're moving along a direction in which these two modes, these two terms, which are exponentially decaying and exponentially growing, otherwise they become of comparable amplitude. So you don't have, so you bypass this problem of having to disentangle these two exponentially decaying and decaying modes. So it is quite useful to compute overtones, and that's why we applied this method. This doesn't mean that one cannot use other methods, such as I think WKB should be fine for doing this calculation as well. And the thing is that the phase amplitude method is more accurate for, as far as I know, from simple WKB, even for the first overtones. But in principle, the same calculation could also be done using continued fractions, for example. But another reason that we use this is just because it's such a fun method, because you have this analytic continuation and so on. So it's and it's a starting point to also learn about more complicated techniques, in particular those ones that allows you to compute the quasinormal-mode spectrum analytic at the limit of n goes to infinity. Those also relies on this analytic continuation procedure. So okay. So basically, to wrap up, it's basically a method that allows you to compute at least the lowest, the first overtones in a very accurate way in comparison with the direct integration method. That will be the very short answer for the question. And it's very general question.
Thank you.
Okay, thank you, Hector, and thanks to all the participants as well for attending this very wonderful seminar. So I guess we are done, and so thanks to Hector again, and hopefully we'll see you again in our future seminars. Okay, thank you, Hector. See you, take care.
Thank you.
Bye.
Okay, bye. Thanks again for the invitation.
Thank you.
Bye.